Welcome. This question says in a heat engine, 14 joules of heat is taken from the hot reservoir, 8 joules of work is performed, and how much heat is dumped into the cold reservoir. So the way we can picture a heat engine is we can imagine it schematically as having a hot reservoir. And then we have a cold sink. And without this temperature difference, there's no driving pressure taking energy from the hot to the cold. So we need this temperature difference. But the clever thing about the heat engine is that it's a mechanism, and a good example would be the steam engine or the internal combustion engine. It's a mechanism by which it takes some of this heat and converts it into useful work. Now, in fairness, eventually the work is used to overcome friction, and friction heats up the environment, so it always ends up at the cold reservoir in the end. But in the meantime, we got something useful out of it. So there's my schematic diagram. I suppose I can also think of it as Q hot, which is the heat coming out of the hot reservoir, is equal to work plus Q cold. Two ways of looking at the same thing. In this case, I have some numbers to play with. So what this says is 14 joules of heat. So this is 14 joules of heat is taken out of the hot reservoir, and 8 joules of work is done. So what is this? And I can say, oh yeah, Q cold is equal to, well, 14 minus 8 leaves 6 joules. So I can actually get it from my diagram. Or alternatively, I could say, well, 14 is equal to 8 plus Q cold. So Q cold is equal to 14 minus 8, which equals 6 joules. And I get the same answer. It's the same thing, of course. My schematic representation mirrors the equation, or the equation mirrors the schematic representation. So there we have the first part done. And then the second part is, well, what's the efficiency? And again, the efficiency is given by my efficiency is equal to what you get out, which in this case is work, over what you put in, which in this case is Q hot. So in this case, looking at my diagram, I would say that my efficiency is what I get out, which is 8 divided by what I put in, which is 14. And if I get my calculator, I see that 8 divided by 14 is going to equal 0.5714 something. And when I look over here, I actually have 57% rather than 0.517. And of course it turns out that 0.57 of 1 is like 57 of 100. And the way we express of 100 is we say 57 per 100%, 57%. So don't get caught thinking that this has to be 0.57%, because it's not. It's just 0.57 of 1 is the decimal of this fraction. 0.57 of 1, which is the same as 57%. People, sometimes in class I'll ask people how efficient various engines that we're familiar with are, and one of the shocking things is that a traditional car engine is not particularly efficient. It's something like 30%, not particularly efficient at all. An awful lot of energy goes up the tailpipe. Year by year it gets better, but engines are built for power, not necessarily efficiency. So there we have it.